Okay, so today's lesson is about modems, modem concept and methods. I'm going to talk about our subject today, and then after I tell you which chapter of the book you are going to, you can read to supplement for the subject today. So I'm going to talk about modem concepts and methods. So I'm sure you all heard about modems. So if you remember, we started by talking about uh, sending and receiving data, and then we talked about different kinds of modulation, right? That means how I'm going to send my data from point A to B. Then we talked about different kinds of modulations. And then at the end, I started talking about digital data and said, okay, so how am I going to send a digital form of data from point A to B? Then I talked about different modulation techniques. So I'm going over in today's lesson over them. Why? Because modem, what is a modem? Modem by itself is the device that can transmit and receive data, and it can modulate your data and send it. And then it has demodulator, which can receive the data. This modulation part I want to talk about today to see what different kinds of modulation are available to us. Um, for example, if you want to send, for example, over telephone lines information, or cable TV, or coaxial cable, wireless, um, you want to send the wireless data, which modulation we are you going to use? So again, I start by talking about modem, and I said that modem consists both of modulator and demodulator. So modulator is like putting your data on a port of transformation, means of transportation. For example, put your data on a taxi, if you remember the analogy, or a plane, and send it. And then demodulation is just get your data out of that signal that has helped you to send the data. Okay, so you put it on top of a signal to send it, that's modulation. And then your data is on top of a signal. Demodulation takes your data out of the carrier signal, basically. Both of them, demodulator and modulator, both exist inside your modem. And modem can simultaneously transmit and receive data. So it's like a full duplex operation. Okay, so that's the modem. Again, for you to remember, the analogy would be is like a place that you can take a cab and the cab can drop you off. That's the modem. Now, there are different kinds of modems. There are four basic types that exist. The first one that is not that much used anymore is called analog modem. So it's low speed analog modem. This one is not used that much anymore. The digital ones are more popular. DSL, I'm sure you have heard DSL. It stands for Digital Subscriber Line Modems. This is one kind of modem. The other one is cable TV modems. And the next one is for wireless communication, wireless modems. Okay, so these are different kinds of basic modems. And then by now, you know that there is like a modulation happening for data communication. So there are, again, 4 main types of modulation that modems are using, that are using modems. You have an idea when I talk about, for example, FSK, you know that that's short for frequency shift key. And I'll talk about more frequency shift keying later, but you have already heard about them, right? So the ones are one frequency, the zeros are another frequency. That's frequency shift keying. So that's one way of sending your data out, frequency shift keying. There's another one that is called PSK. It's phase shift keying, PSK. Another one that is very that's important for you to know, and I'm sure you have seen it because I've heard one of you talking about in one of the assignments or presentations about QAM, quadrature amplitude modulation, that I will talk about this today a lot. So you learn about QAM, which is very important topic, and it's good to know in general for your common knowledge. QAM, quadrature amplitude modulation, is a kind of modulation that is used in modems. And the last one is OFDM, orthogonal frequency division multiplexing. Again, I'm talking about different modulation types, and I'll talk about most of them. I'll talk about these 3 today: FSK, PSK, and QAM. FSK and PSK you already know, I assume, but I'll go over them regardless, and then I'll talk about quadrature amplitude modulation. Okay, so FSK, you know already, it's a type of modulation, and because we are now talking about digital information that I want to send, 1 and zeros, because we are in digital world, right? So how would FSK work? I said for ones, we use a higher frequency, and then for zeros, you have lower frequency. The amplitudes are the same. So ones are more tight, higher frequency, zeros are lower frequency. So this is how you would, the modulator at the end would know which is 1, which is 0, okay? So in short, FSK, 2 sine wave frequencies are used to represent binary 0 and 1. For example, you can use for 0 and 1 for telephone audio bandpass. 0 is usually 1070 hertz. That's the frequency. Here I want to talk about jargon words that they use for 0 and 1. Usually they call 0 the space. If you hear it somewhere, it's just another name for 0. And for 1, they use mark. If you hear mark, so it's like a space mark. That means 0, 1. And for telephone audio, 1270 hertz is your ones. Okay, so you have 2 different frequencies. One is higher than the other one. And so for telephone, it's full duplex, right? So you're sending data and receiving data. So you need 2 different set of frequencies for transmit and receive because it's full duplex. So full duplex, by full duplex, I mentioned this before, that means you're both transmitting and receiving data. So 0 can be 1070 hertz, and 1 is 1270 hertz. That would be your transmit or your origin signal. Then you are waiting for a response. The response can be 0, can be another. It's 225 hertz. I talk about these numbers because then I want to show you what's happening inside the modem. So, and then 1 would be 225 hertz. Feel free to interrupt me if you don't understand anything or you have any question. So that will be for my transmit. That will be for my that will be my original signal. That would be my answer. Okay. So I have two different kind of frequencies. All of these frequencies are inside the telephone audio bandpass because it goes from 300 hertz to 3 kilohertz. So you have a bandpass of frequencies that are used. Now, what's happening inside the modem then? So these frequencies are for modulation. So if you look at the modem itself, I said you have a modulator inside, right? So FSK modulator, in this case, FSK modulator. I'll talk about different kinds of techniques, but let's stay on FSK. So I have my computer or whatever that is creating 1 and zeros, that goes to FSK modulator, right? This is my modem. That goes into FSK modulator. Okay, so what comes out goes out. So that's your signal. And then there is another modem at the receiver, right? This is another modem that receives your signal. Then it will go to a bandpass filter, which will, I write the number, then I talk about why. So it goes from its 1000 into 1350. So why? Because I said that when I transmit a signal, it's 1070 and 1270. So this bandpass will pass these frequencies and filter the rest. So you're sending your signal, it gets into a filter, and then you have a modulator to get your signal out, 1 and zeros out. That FSK demodulator is here. And then it will go into, for example, a computer that needs 1 and zeros. Okay, so that's one part. Then this modem is responding or answering to the first modem. So you're sending a data and then you want an answer. So same thing. So when I started, I said modem has both modulator and demodulator. So if you want to send the data, your 1 and zeros will go into another, the FSK modulator of this modem. So that means it's now on an analog signal with two different frequencies. Then it will go, because now you have a carrier signal, and then that will go into a bandpass filter of this one that goes from 90-50 hertz. So bandpass filter, that means it's only passing the frequencies from this to this. That's what bandpass filter means. Okay, so it goes from 90-50 to 2300, which is a good thing because that means these two frequencies that I have for my answer signal will pass. So that will go there, and then it will go to the computer. So this should give you an idea about modems, what's happening inside. The thing is that in reality, you don't have two different cables, so it's the same thing. Other than that, by now, you should get an idea about a modem, that you have some data, binary data going out, some one and zeros, go to your FSK modulator. This is one kind of modulation. I'll talk about others later. So it will go, for example, this is for a telephone audio, sending and receiving voice. So it goes, and then with modulation, you can send it through long distances. And then at the receiver, it gets filtered, demodulate, go to computer, and then again, one and zeros go to a frequency shift key modulation technique. It will go on top of a signal with two different frequencies, will go here and gets demodulate. There is a, I'm missing a demodulator here. So there should be a demodulator here, FSK demodulator, and then goes back. Same thing, same idea, same modem, different, for example, houses, okay? So that's the idea of modem. By now, you should know what FSK means and what modem is. And you should know that why I said these analog ones are kind of obsolete today, because most modems now use digital techniques, which makes sense, right? Because they are simpler and they are more adaptable to integrated circuits or IC implementation. Okay, now I talked about frequency shifting here. I started by talking about FSK signals, which they typically occupy, if you remember when I talked about FSK, I said that they occupy a wide bandwidth usually because of the sidebands that they create, because of the FM process. And so there have been several techniques that have been developed to improve this spectral efficiency of FSK. What do I mean by spectral efficiency? That means how well a specific modulation technique can maintain data into a minimal bandwidth. Because bandwidth matters, right? Because you want to occupy as a small bandwidth as you can, so you can have a space for other informations that are sent. So in order to overcome this for FSK, there is another technique called that they developed to decrease the bandwidth, and it's called CPFSK. It's FSK with one CP here. CP stands for continuous phase frequency shifting. Why this is important? Because when you remember, I talked about FSK, I said, okay, so you have one and zero, so you have two different frequencies, right? But what about the phase? Is the phase here continuous, or you have some, for example, this ends here and the other one ends here? There is no there won't be any phase coherence sometimes, and there will be abrupt changes in your signal during 0 to 1 and 1 to 0 if you're not careful with the phase. There will be glitches. These are called glitches, which are not good. Why? Because that by itself can produce harmonics. That would be a frequency by itself, and that will produce harmonics, which will result into higher bandwidth. And another thing is that it can make the demodulation basically more difficult. and as a result produce more bit errors. So because of that, this new technique on top of FSK is called continuous phase. And it's so what they do, they want to get rid of these glitches with this method. They want their signal to be coherent. It's very important to have like a smooth transition from your 1, for example, to 0, right? You want it to be smooth. You don't want any glitches like this. That's where CPFSK comes from. So I don't go over how they create this, but that's the idea. So when you have CPFSK instead of FSK, that means that your transition is smooth, okay? So it's a coherent version that use less bandwidth. That's the idea. I want to use less bandwidth and better reduction of noise. So that's an evolved version of FSK. And it's not only for FSK, even for OOK, on and off keying that I talked about before, it's important to have like a coherent signal to avoid that abrupt changes. Even for ASK, amplitude shift keying that I talked about before. So they have techniques to get rid of these glitches and make sure that the signal is coherent. If they apply those techniques, it's called coherent phase, which the name makes sense, right? Coherent phase, and then whatever shift keying technique that you use. Okay. So this was extra for you just to know that there are improved versions of FSK. But the idea is the same. It's frequency shifting. And the idea is that to have coherent signal at the end of the day. So that's FSK, right? That's FSK, frequency shifting. And I not only talked about it again, I applied it inside a modem. Okay. Now, what about PSK? What is PSK? So PSK stands for phase shift keying. If you remember, I think I talked about it before. Phase shift keying. And whenever I talk about any shift keying technique, that means ones are defined one way, zeros are defined in another way. So in this case, the binary signal to be transmitted changes the phase shift of a sine wave character, depending upon whether 0 or 1 is transmitted. You have different phases. There are different kinds of phase shift keying. If I want to be more precise about phase shift keying, there is a BPSK, which is called binary phase shift keying. You might think by now, oh my God, look at all these different techniques. But for you, at the end of the day, you should know what is PSK. You know, you don't need to know all these different methods, but you should have a general idea. For example, you should know, okay, I know FSK. That's easy for me now because it's frequency shifting. 1 is one frequency, 0 is another frequency. And then you have an idea, okay, what does this CP does here that will make it more smooth so I have less glitches without even going into detail. So you should have a general idea of all these modulation techniques. For example, phase shift keying, if somebody asks you what is phase shift keying, you at least know, okay, I'm sending 1 and 0. Ones have 1, and I know now that I'm sending it with an analog signal, right? You know that by now. And for 1, I have one phase. For 0, I have another phase. By phase means where the signal starts. And then, of course, they all have their own sub versions. BPSK is binary phase shift keying. There is another one, is differential phase shift keying, DPSK, which stands for differential phase shift keying. These are the modified versions of PSK. So binary phase shift keying, what is BPSK? Binary phase shift keying. So during the time that the binary is 0, the carrier signal is, as I said, transmitted with one phase. When it's 1, the carrier is transmitted with another phase. You know that, but for binary, if there is a phase here, for 1, that would be that phase plus 180 degrees phase shift. So there is a definite value for the phase shift. If this happens, you have binary phase shifting, okay? So whatever phase you have for your 0, then for your 1, you have 108-degree change in phase. That's BPSK, 180 phase shift. When you hear BPSK, just think about 180-degree phase shift. Now, what about DPSK? I talked about DPSK, which is differential phase shift keying. Now, it's a version of binary PSK that I just told you. It's called differential. And the thing is that when you demodulate DPSK, there is no reference for your phase. You look at the signal before, and the signal before that will be your reference in terms of phase. So there is no carrier phase reference. You don't have a reference. Your reference is, that means that the phase of the received bit is compared with the phase of previously recovered bit in general form, okay, without going into detail. That's DPSK. For DPSK to work, for it to work, before making it, the original binary bit stream has to go over a process known as differential phase shift keying. Okay, so what does it mean? So let's say you have a serial data input. That means you are sending 1 and 0s. Okay, it goes to exclusive NOR gate, and then it will be multiplied to a carrier, and then it's actually the output will be returned with 1-bit delay, and that will be 1 input of exclusive NOR. Okay, so what it does is it's comparing the previous bit this one bit flip flop, I don't know if you remember from digital, you can do that with a clock flip flop. And exclusive NOR, if you remember the table, it's actually 1001. So what it does is that it's comparing your output to the previous bit. Let's say these are previous bits. If they're the same, the output is 1. If they are not the same, the output is 0. So it's comparing, it's basically comparing your bit with the previous bit. And then if you want to, so that's what I mean by comparing your output bit with the previous bit. So the output will be fed back, and then it gets compared to the input. Gets compared. So when you have 1 bit delay, that means that your new input will be compared to the old input. And if they are the same, because it's exclusive NOR, your output with 1, and if they are not the same, your output would be 0. So that's the basic function of DPSK. That means that every bit will be compared to the previous bit. That's the idea. And I just explained this so you would know that there are devices to do that, and give you a general idea of what I mean by DPSK. And then the demodulation is accomplished by same thing. You multiply the carrier to 1 bit delay, and then you have low pass filter, and you recover your binary data. Let me see. Any questions so far? I think at the end it might be a bit confusing, but what I talked about, guys, so far, what you have to know is what is a modem. If you understand, oops, these are my C++. So you should know what is a modem, and you should have an idea about FSK and PSK in general. The rest was just for your common knowledge. Let me see the questions. You follow? Okay, good. So I'm not sure. Is it too much or you're okay? Okay, good. So I can continue, right? Okay. Okay, good. So let's continue. Now let's go to QPSK, which is the kind of a new topic for you. Okay, so before starting with QPSK is that I have to, so why we need QPSK? Because the main problem with BPSK that I talked about and DPSK that I also talk about is that for each bit, in other words, the speed of data is limited, right? Because you are trying to assign a part of your signal that you're sending into only 1 bit. And it's working, but what if I assign this part of my signal? So far what you have learned is that, okay, I either change the amplitude, it's ASK, or I change the phase, it's PSK, or I change the frequency of this signal, a part of this signal, it's FSK. Okay, you understand all of that, but it's working. But I want to do more. How about I put on in my cab, or in this portion of my cab, more passengers? How about I put 2 bits here, 3 bits here into this part? If I'm able to do that, then I can send more data, right? So what I'm trying to do is to increase the binary data rate. Okay. And I want to do it without increasing the bandwidth. I don't want to use more bandwidth to increase the binary data rate. So what I'm going to do is I want to encode more than 1 bit per, for example, for this case, per phase change. So you have another types. Whenever you see Q, it stands for quadrature. And quadrature, what it does is that it's using 2 signals, sine and cosine, and it sends some bits with sine, some bits with cosine, and then it's just a general form. I'll explain in detail. Then it mixes them, makes them one signal, and then send the data. So you have a signal that is combination of or adding of sine and cosine, and then your information is there. That's when you see Q, that's what I mean. But I'm using quadrature, or what you are going to see. The idea is that I want to put more data. I want to increase my bit rate, okay? So again, so far you have seen that for any modulation I talk, that the speed of data is limited, right, in a given bandwidth. So let's use an alternative way to use combination of 2 or more bits to specify, for example, for this case, a phase change. So that means my goal is that phase shift, I want my phase shift to represent multiple bits. So I want my phase shift to represent multiple bits, which is pretty cool, right? Why we haven't thought of it so far, that let's use more. So one phase shift, multiple bits. So one commonly used system for doing this is known as you see, QPSK, or quadrature phase shift keying. Okay, so how would this work? In QPSK, instead of only 1 bit, as I said repeatedly so far, each point of successive digital bits is assigned a particular bit. Then you can put different number of bits. I start with a pair of bits. So that means, for example, I put 0, 0. For 0, 0, I assign one phase. For 0, 1, I assign another phase. So if I want to use 2 bits instead of 1, just another jargon I want to talk about is called dbit. It's just when I talk about each pair of bits. If you see something like that, that means each pair of bits. So if I want to assign 2 bits into my phase shift, I have 2 bits. So what combinations I can have? I can either have 0, 0, 0, 1, 1, 0, 1, 1, right? That's all the combinations I can have. Then I can assign phase shift to a pair instead of 1. So when I have 0, 0, I have 45 degrees, for example, phase shift. If I have 0, 1, I have, for example, 135. 1, 0, Um, I'm going to write it in a grade code manner. I'm just changing one bit. So 1, 0, I'm going to assign 2 to 5 degrees, for example. And this 3, 4, 5, phase shift. These are all phase shift, right? So you have it here that instead of assigning one phase shift to one bit, I'm assigning phase shift to 2 bits. So I'm sending more information, which is pretty smart, right? I can even increase the number of bits and then send more information. And because I have 4 different ones, 4 different phases, they usually, like in general, regardless of number of bits and phases, they show it in a form of phasor to in order to make it clear to the user what kind of modulation they are using. For example, when I have when I'm sending two when I'm sending 2 bits, this is the phasor. By phasor, that means I have amplitude of my signal and phase. So I said I have 45 degrees for 0, 0. Then that would be 1. Then I have 4 different phase. So I have 45. I have, I said 350, which is from here to here. I assigned 1, 0 to it. For 1, 1, I have 225, which is this angle. And for 0, 1, I have 135 degrees. Okay, so um, this is called constellation diagram. And depending on the number of bits, you have different points on the constellation diagram. Because you only have 4 points, in order to basically spread them equally, for this case, I have 90 degrees phase shift between 2 angles, right? So I have 90 degrees phase shift from 45. That's why these numbers. So whatever you start with, the next one should be 90 degrees. 90 degrees phase shift, 90 degrees phase shift. So again, what I did for QPSK, instead of changing the phase for one bit of information, for this case, as I said, you can increase the number of bits. Here I'm showing you 2 bits of information. For 2 bits of information, I am changing the phase accordingly. And this is all the combination I can have. I cannot have anything other than what I wrote here. So 1, 0. Actually, this is, if I do this, I'm changing 2 bits, right? As I said, I want to do gray code. So if by gray code, I mean I'm changing 1 bit of information. So if I'm changing 0 to 1, this will be 1, 1, because I'm changing only 1 bit. And here, I am going to put 1, 0. When you use gray code, you will have less when you're using only 1 bit, you decrease your error usually. So that's called gray code. That means I'm sure you have seen it in digital electronics, that instead of going from 0, 1, 2, you're changing 1 bit. If you remember from Karma map, we were just changing 1 bit and we were using gray code. It's the same thing here, basically. So I have 0, 0, 0, 1, 1, 1, 1, 0. And but in terms of electronic and modulation, this is a very smart way of sending information and using and increasing the bit rate, as you see. So it's pretty cool. This is very common, and like these angles that I'm using are common ones, 45 degrees, but it's not like written in a stone. Other phases can be used. And they, as you see, for 2 bits, you should have 90 degrees phase change. So in constellation diagram, you have a nice 2 bits transfer of information. Okay, so that's QPSK that I talked about. Now, so I'm going to do a summary. So I talked about QPSK, and I said that the phase shift can represent multiple bits instead of only 1 bit. And because of that, my bit rate of data transfer can be higher than the term is called baud rate. Again, it's another jargon. If you see somewhere, it's called baud rate or symbol rate. So that means you're changing. Baud is like means symbol. So when I say that more bits per baud are encoded, that means more bits per symbol, like phase change or amplitude change, is encoded. That's what it means if you see it somewhere. And okay, so I went into QPSK in detail, and I talked about constellation diagram, which is an important concept. You see it a lot. And the length here is the amplitude of your signal that you're sending, okay? Because don't forget, it's all analog, like bits on top of the analog signal, right? So this is the amplitude of your signal, and 45, these are the phases, different phases. So you have 4 phases to send 4 different combinations. Now you, before going forward, you either see it like these lines, or usually they just show them with dots. It's the same thing, okay? Okay, now, what about, you might say, okay, I understand it, but how would you do it? What is the circuit? How would the circuit look like? So it's very interesting. Like you are sending 0 and 1s, right? You're sending bits of information. That's the idea. You're sending bits of information, and the idea is that to somehow at the end have 2 bits together, going together, basically. So you want these 2 to go together, these 2 go together, and so on. Okay, so in order to do that, when you look at the device that does this, there is a bit splitter that is here. And what it does is sending even bits. What do I mean? So usually when you look at the books, they say they send even bits here, odd bits here. So what does it mean? That means that these bits are all in line, right? So for example, this is what I'm sending. I'm sending 0, 1, 1, 0, 1. So the first bit here will go here, and there's a shift register here. And the next one will go here, or vice versa. The idea is that they get a split. And then as the shift register sends more bits, then the one goes up, the other one goes down. That's the idea. One by one, they go and sit on different signals to be transmitted. And then here you have a mixer, which by mixer I mean that you have your cosine signal or sine, cosine signal. So you have your analog signal that will be mixed with your bit information, in this case 1 bit, and it will go here. Okay, so what's happening here? So you have, for, remember I talked about BPSK. I said 1 bit of information if there is one phase. So let's say I have cosine of omega t. If that's assigned to 0, then cosine of omega t plus 180 degrees will be my 1, which mathematically that will be minus cosine of omega t, right? So phase shifting is happening for this one, for cosine of omega t. If the phase is 0, it's 0. If the phase is 180-degree phase shift, I'm sending my 1. So it's BPSK happening here in this part. And then what they do, it's just for 1 bit, right? There's another bit coming here, which is, it's going to sit on sine of omega t instead of cosine of omega t. Sine of omega t. That means that this cosine of omega t is 90 degree, has a 90-degree phase shift with sine of omega t. Okay, so the carrier for cosine is different, for this bit is different than this bit that's coming here. This is cosine, this is sine. Or whatever carrier I have here, it has 90-degree phase shift from this, because cosine of omega t plus 90 degrees is sine of omega t. Okay, so then this 1 bit will do BPSK to my sine of omega t. So that means sine of omega t will be 0. And this is sine of omega t plus 0 degrees, right? So the phase shift, if this is 0, then sine of omega t plus 180, which is minus sine of omega t, will be my 1. So this one has a different phase of this one. So I can assign this to 1 binary, 0, this one to 1. Okay, so each bit is sending, I'm sending them in parallel, simultaneously. I'm sending them with different carriers. And at the end, I'm going to add them and then send it. So this is my QPSK. QPSK is coming out. So this signal plus this signal will come out, and the signal, which is the summation of whatever is coming from here and here, has the information of these 2 bits on them. One is on the cosine part, one is on the sine part, and they are added together and they are sent. And for example, so the beauty of this is that for 1, 0, when you add them, you have one phase. Then for 0, 1, when you add them, you have another phase. I actually, when I was preparing my course notes, I went with MATLAB and just simulated 2 different ones of these cosine and sine. And I saw that, for example, if this is 0, 0, this is 1, 1. So 0, 0 has a different 90 degrees. So this is 0, 0, this is 0, 1. So what you have at the output, you have 90 degrees phase shift from those 2 signals. So you would know, okay, so this is my 0, 0, this is my 0, 1. And then 1, 1 has another 90-degree phase shift, and 1, 0 has another 90-degree phase shift. So you always have phase shifts, and each 2 pairs have a different phase shift from the next 2 pair. And when you have only 2 bits sitting on different signals, the difference between different a combination of bits, they all lie into the phase of the QPSK signal that you get out. For example, from what I said so far is that, for example, when you send 0, 0, what does it mean? So 0, 0 means that I am putting my cosine of omega t, right? I'm sending 1, 0 with cosine of omega t. I'm sending another signal with sine of omega t. And then I'm adding them to get a signal here, right? And then, for example, 0, 1, 1 is, so 0 is cosine of omega t, and this is sine of omega t. If you remember, 1 should have 180 phase shift with cosine, right? So your signal will be flipped. So that will be flipped, and 0 will be the same, and then you add them. And then whatever you get here, whatever signal you get here has a 90-degree phase with the signal that you have here. That's the idea. They are 90 degrees out of phase. That's when you have 2 bits, but you can encode more bits per phase, then you can produce higher data rate. So you can have, for example, 8 PSK, okay? You can have, so for 8 PSK, that means you have how many bits? You have 3 bits sending, right? Because 2 power of 3 is 8, so you have 8 different combinations of data that is sent. Let me pause this. Okay, so for example, as I said, you can have 8 PSK. If I tell you 8 PSK, then you automatically would know that I'm talking about 3 serial bits. And that will produce 8 different phase change, because it's I'm talking about PSK. So when you hear something like 8 PSK, you would know, okay, I have 3 bits, and I'm assigning different phase change for even higher data rate. And then when you look at the constellation of this, for example, then it will be different, right? Even for 4-bit number. So if I have 4 bits number, then I have 16 PSK. So that means you have more dots on your constellation, like 16. So, but so far, the amplitudes were the same, right? I didn't change the amplitude. And all the dots fall on a circle. So far, when you look at this, when your constellation diagram looks like a circle, you would know that it's a PSK method. But what about if I change the amplitude? So that's another subject, which is called QAM, which is short for quadrature amplitude modulation, and this uses both amplitude and phase modulation. So not only it creates phase shifts, but also the amplitude of the carrier is varied. Okay, so now that you have an idea, you would know, okay, so she's telling me the amplitude, so the constellation, for example, if I have 3 bits, so for 3 bits, I'm sending, I have 8 different combinations, right? but instead of having more dots, 8 dots like this, you can have it like this. So you have 2 here because the amplitude of this is different than that. Then you can have 2 here. Then you can have 2 here. And you can have 2 here. So for example, if this is 110, this is 111. For 3 bits, I have 8. 1, 2, 3, 4, 5, 6, 7, 8. This can be 010. This can be 011, 001, 000, 100, 101. Okay, so this will be the constellation diagram for QAM. Okay, so how would this work? How would the circuit for sending QAM work? You already know how would this works, PSK, QPSK. What about QAM? Okay, so for QAM, first of all, another thing that you see in the books is that the signal that they are modulating with cosine, they are called I, and this one that you are sending with sine or 90-degree phase shift carrier signal is called Q. So you're sending IQ, IQ, IQ. Now, let me talk about, for example, let's say I want to send 4 bits of information with QAM. So you say, okay, 4 bits, so it's 2 power of 4. I want to talk about that means 16 QAM. So the number is usually here, so you would know. So I'm sending 4 bits of information in one, basically, portion of my carrier signal. So I'm having four different bits. Now, what I do is, so here I said I will go up, Q will go down, right? So if I call this I, and I'm going to call this, maybe get it better. So I'm going to call this I, and this is my I as well, and this is Q, this is Q prime. That means I'm sending these two up, and I'm sending these two down. So I'm sending 2 bits of information up, two of them down. Now, what do you think will happen? So it's pretty cool actually. I'm sending the phase with one of them, changing the amplitude with the next one. I'm changing the phase of my carrier with one of them. I'm changing the phase of my, so amplitude change, phase change, amplitude change, phase shift. So I give them tasks. So these 2 bits of information, one bit will change the amplitude, the other bit will change the phase. One bit will change the amplitude, the other bit will change the phase. And what comes out here is like phase amplitude modulation, phase amplitude modulation. They get mixed, and then they will be sent to transfer my data. So it's a very smart way. So to make it more clear, I'm sending I and I prime with one, with my cosine, right? So what do I mean by that? I have I and Q. So I think if I write it like this, so I have I prime, I prime. So I said one is polarity. That's what I said, right? And I said one is magnitude. Okay. And so I'm sending them top here. I'm sending them on in this route to go with the cosine. And Okay, so before going further, I have 2 bits. At the end of the day, these are only bits, right? So I have I print, so these are the only combinations I can have. 0, 0, 0, 1, 1, 0, 1, 1. These are the only combinations that I can have again. So I said 0 and 1s are magnitude. Then it's up to the design. Let's say I say, I want my 0 to be low voltage. For example, 0. If you see 0, make it 0.2 volt amplitude. If you see 1, make it, for example, almost 1, 0.8 volt. Okay, so my 1 has a higher amplitude than my 0. And then this is the polarity. 0 will be 180-degree phase shift, right? So that will be my minus cosine theta, cosine minus cosine theta, and 1 is just my cosine theta. So in terms of polarity, that's in terms of amplitude. In terms of polarity, I define it this way. I say if I have 1, send it with cosine of theta. If I have 0, cosine of theta plus 180 degrees, so send minus cosine of theta. There is a phase change between those two signals, and these are the amplitudes. Now, when your converter here will look at I print and I, then it will say, okay, so that means 0, 0, the polarity is 0, so that's minus. So that will be minus 0.2 volts. So minus 0.2 cosine of theta will be sent. If it sees 0, 1, minus, the magnitude is 1, so 0.8 cosine of theta will be sent, or cosine of omega t will be sent. If I have 1, 0, the polarity is 1, so it's cosine of omega t, but the magnitude is 0, so I have 0.2 volts. What about 1, 1? It will be 0.8 cosine of omega t, right? So depending on the pair, that will be only for my I part, but I'm sending 4 bits. So I have to do the same thing for Q prime. Again, I can say that I can assign 1 to amplitude, 1 to phase. So I can say, for example, Q is my polarity, and Q prime is my magnitude, and these are only bits. So as I said, at the end of the day, these are only bits of information. So 0, 0 will be minus 0.2 cosine of omega t, because the polarity is 0, so it's minus. The polarity is 0, but I have for magnitude of my amplitude, this is the maximum. So I define it as 0.8 volts. So that will be that. And then 1, 0, the polarity is 1. So, but the magnitude is a small, 0.2 cosine of omega t will go. And here I have 1, 1, the polarity, and the magnitude is 1. So polarity is 1, magnitude is 0.8. So this is what goes now here, and then they get mixed and will be sent to, okay, now that you have an idea of how 4 bits is sent, I can draw my circuit. So as I said, I'm sending 4 bits with a shift register that you know already what is a shift register from your digital course. So it's going, 2 of them are sent to this module is called 2 to 4 level converter, just because you have 2 bits and you can have 4 different combinations, right? So it will convert it to whatever it is. That's why it's called 2 to 4 level converter. Same thing here. You have 2 bits, you can have 4 different combinations. So you have 2 to 4 level converter. Okay, and then what comes out is called PAM because it's phase amplitude modulation. Phase amplitude modulation. It comes out, and then as you know by now that it has to sit on a cap to go, so there's a modulator here, and I said for QAM, one of them is sine, the other one is cosine because they should have 90-degree phase shift difference. So whatever you are sending here, the carrier here has 90 degrees phase change. So if this is cosine, this is sine. And then they go and they get the summation of them will be sent. This signal that is coming out has the information of these 2 bits and these 2 bits, which are encoded into amplitude and phase of the cosine and amplitude and phase of sine. So because I have 4 bits for this particular example, this circuit that I just drew for you is called 16 QAM. Quadrature amplitude modulation. Okay, so how would the constellation diagram would look like? For a constellation diagram, you would have different amplitudes and phases, and because you have 16 points, you're going to spread them like this. And for example, this is 1, 1, 1, 1. This is 1, 0, 1, 1. This is 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0. You see, each of them has a different magnitude, amplitude, and phase. So it depends on where it is on the constellation diagram, gives you an idea how each 4 bits is getting demodulated. So you know in advance, if you get a signal, part of the signal with this amplitude and this phase, that will be 1101. 1001, 0001, 0101, this is 0000, this is 0100. Something like this, okay? For example, if you send, for example, 0000, if you send 0000, okay, with whatever amplitude I just did, so that means that you have minus 0.2 cosine of omega t for this part, and then you have minus 0.2 sine of omega t for this part. So you're sending this. And if you do the math and add them and use trigonometric identities, at the end you get something like this. For example, sine of omega t minus 135 degrees. So if you come here, that will be this signal. Ugh. That will be this signal here. Okay, so they're all in harmony, no matter where you look at them. If you look at this circuit, this is the constellation diagram. And where did they get this? From adding the different signals, sine and cosine, that you get from here.